Hello everyone, and welcome back to another session on simulation. So what have we done so far? We've done first order systems by scripting. We've done some Simulink modeling. We've also done some Simscape structures, and to add to that, we've also done a little bit of SolidWorks motion analysis. All three together so far. What we've actually not done is we've not covered any sim mechanics, or well, now it's called SimMultibody, but formerly known as sim mechanics. We've not covered any of that yet, and I think today that's what the real plan is, to try and close the loop and show you the functions of how this works. Conventionally, at first, it's a little bit confusing, a little bit frustrating, but what we're going to do is make very small steps and then slowly show you how this thing works. So here goes. Right, so I'm in MATLAB. What I'm going to do is go new, Simulink model. Obviously it takes a couple of seconds for it to load up, purely because, if you remember, Simulink is a bolt-on, so it's actually loading an extra bit of software. So what I'm going to do is go blank model, and if you remember, this is our workspace for essentially where all activity happens. All simulations take place within the workspace. We can have multiphysics, where we can have simpler mechanical structures interfacing with fluid type structures, or fluid simulations, let's say, and we can look at the dynamic impact on that. As I've said before, in this series of videos, what I want to do is perhaps grow to the point where we can even take a microcontroller, take that feeding data, put it into the simulation and get something working. What I was planning on doing is perhaps a linear actuator, a servo, something straightforward, just for you to see the basic principles of how this functions. But what we need to do at the minute is really focus on using this as a tool. So I've clicked onto the Simulink library as normal. Now, if you remember, I'm just going to shrink all this down because, as you can see, I've been messing around already. When you load up, that's typically what you'll find. Now, don't forget, for navigation, come down to Simscape, and when you open up Simscape, you will get the standard options as normal. What we're going to be doing is focusing all our efforts on multibody. And I'm just shrinking these down because I was just navigating to some of the new tools today, which is another topic entirely. So let's get to modelling our mass spring damper system. Right, so from multibody, we need to establish the ground. Don't forget, we need to say where our starting point will be in any type of CAD system, simulation system, any computational fluid dynamics problems. You always need to define what your reference geometry will be, where you're going to come from. So what we do with this is we define a world, or a ground, or a start plate. In essence, this would be our 0, 0, 0 marker of what we would see in any CAD system. So I'm going to click Utilities, and in Utilities, what we need to do is we need to say, right, MATLAB solvers, we are super happy with them. We're going to use what MATLAB has to offer as solvers, so we're going to drop in a solver configuration block. If you remember from past discussions, solver configuration blocks will allow us to change. We can update it, we can change it into all different types of configuration parameters. Phenomenal bit of kit. But what we will do with this is we're going to assume that the solver configuration is going to do the job for us. Basically, we're trusting MATLAB, and I think after their sort of results, I think we can do. So let's push on. So now we've got this. What we now need is, if I come down, see I'm entering multibody, drop all the way down, get to Utilities. In Utilities, if you remember, we need something that will define our relative tolerances to when we're solving. We need something that will give us orientation of gravity, where gravity will sit. Don't forget, in any types of these simulations, everything is defaulted to Z. Z will act purely as our gravitational aspect. It does not shift in Y. All rotations, all prismatic behaviors, all appear in Z. So keep that in mind, because it will help you as you're going through. So let's drag that in. It's going to flip that up. Remember, Control and R. So we connect them two up. I will show you a personal thing that really irritates me at some points, but let's just keep pushing on. Right, so if I just double click, just want to check everything that's in there. We've got the linearization for our delta being at 0.001. That for me, because the nature of this simulation is not the most complicated one in the world, we're going to stay with that. That will suit us fine. We're going to have the constant. Interestingly, if you are wanting to drop something from the stratosphere and then enter Mars's atmosphere, anything like that, you don't have to go with a constant. You can go with time variant, or you can change everything about the gravity as much as you like. You can even make gravity a variable if you wish. So as time emerges, it will change with it. It's great what you can do with it. But what we'll do is we'll leave it in Z. In fact, for the whole simulation, let's just stay in Z. Let's make that as simple as possible. So I'll click OK. So just to reiterate, I've not changed anything. We just had a little bit of an introduction through the actual block itself. Finally, we know where gravity is. We know how we're going to solve it. We know our relative tolerances. If I go into the solver, we know that it's going to be using the backward Euler methodology. A lot of people will always claim that Runge-Kutta will be the best way in this case, but funnily enough, a localized solver of a backwards Euler is actually a little bit better in this case. But don't forget, with MATLAB's ability to use all different types of ODEs, and using, if you notice at the bottom, I've got variable time step already set. It means that if it hits a point and then says, whoa, well, that's not quite right, what it will do is look at other options to see if one is statistically more likely to emerge. This type of simulation, phenomenally good news. So, finally, to really establish where our 000 marker will be, our starting position will be, we're going to add a world frame. So I'm going to drag this in, and we're going to have a little bit of a breakdown to this in just a second. So I'm going to spin that round. These three are going to connect together. Whoops, that didn't go so well. Like that. Again, like in Simulink, you left click, drag, and just connect them, wiring them together. So I'm going to double click into world frame. So you see here, provides access to the world or a ground frame, a unique motionless origin, basically the origin of where you're going to come from. It's really useful is the world frame, because if you're going to monitor the position of something, what you can actually do is you can use another world frame and say, right, for this measurement, I'm going to use the starting position of wherever my projectile or whatever it is coming from, and it will measure between the two, giving you an absolute result. Not absolute. Yes, an absolute. Yes, an absolute result. Sorry, it's early in the morning now. Anyway, so let's push on. Now, the differences that we're going to face. There are some differences. First things first, let's have a bit of fun with this. So, what I'm going to do is I'm going to go joints. Now, if I grab a mass, if I hold the mass, then I let go of the mass, it will drop relative to gravity. Mass times acceleration. So it will literally drop until it hits its stop point. Yes? Yes. So, as I drop it, we're not going to model any ground around it, so basically if I dropped a mass, it would just fall for infinity and beyond. Sorry. So these joints are here to replicate specific behaviors that we're trying to recreate. Now, the nature of the mass spring damper is linearized format, so it will just bounce backwards and forwards, backwards and forwards, backwards and forwards, as we know. So what I'll do is I'm going to drag and drop a prismatic, because when we drop it, it goes straight up, straight down. Hence a prismatic motion. So I'm just going to spin that round. I know some of you were thinking, yeah, but sometimes it's not 100% clear. So I wanted to be 100% before we even moved on. Because think about the mass, I'm dropping it, and then it has a motion that will occur to it. Now, this world frame will imply where my 0, 0, 0 is. Technically, when I run this, if my 0, 0, 0 is a present state position, it means that as I drop it, it's going to go to a negative. Think of it of an orientation before or after the datum. So in CAD, for example, if you draw behind the datum, you may be, I don't know, -10 in X. Something like that. So it's important to keep these things in mind. Right, so let's just bring that down. A little bit like that. So we have the back, we have the base of the actual connector. Best way to see this is the base of the connector will be in essence relating to what it is that you're connected to. So in essence what it's saying is the base is these two are related relative to each other. So the base is relative to the actual orientation from the ground, which makes life so much more easier, well, in some respect. The beauty is with having something like this is, what if your ground's moving at the same time? What if you were doing a double mass spring damper? What if you were doing a suspension system? What if you were doing a landing gear? Everything's moving around, and all you're saying with this base is let's make it relative to what it's connected to, which makes the freedom of being able to move things so much more easier, because in essence nothing is restricting you. You are in pure control of what's going on. So let's press on. I do my very best not to be enthusiastic with this, but I make no promises at all. So I make no promises at all. So we have our prismatic motion. If I go back to the mass, what I'm going to do is bring in, sorry, back, we've not even been on it. If I go to body elements, in here, conventionally, just for your notes, over the past few years, these blocks, variable masses, flexible bodies, these were all something brand new that has been emerging slowly and slowly over the years. It was conventionally just solid, and you were forced to model the process. So flexible bodies, just your basic bending moments. We will visit some of this, because the beauty of running these types of videos is I can go as deep as I like, and then it's entirely up to you as to how much you want to look at. So I will try and exploit as much of these as possible to give you an insight as to what each tool does. So let's drag and drop a solid. This is going to be what will be our mass. So if I put this just above the prismatic, and then let's model a mass. Whoops. So as it comes in, you'll see the minute it's bloody gigantic. It's 1 meter by 1 meter by 1 meter. It's huge. So I've changed my units to millimeters, and let's just do something, Stan. Let's go 50. You'll notice the modeling process is purely by a component. So we go 50 by 50 by 50, and I'll just do a zoom to fit, and that's our mass. Let's just take a little deeper look on something else. You'll notice when we did it on SimMultibody, we did it on SimScape, and we also did it on SolidWorks, and we did it in Simulink, and we also scripted this process. You'll know that defining the mass can be such a pain in the arse sometimes. So, however, here it does not care. What it actually is interested in is the density of what you're doing and the geometry that you're using. So let's go 8050. Which I think is I'd have to double check. I think it's a steel. Right, so with a new density, the system does need to know what the new elements are. Now you see here it's derived values. So if I update my derived values, you'll notice that the mass relative to the actual component is right. Centre of gravity is at 0, 0, 0, as it should be, and the moments of inertia have all been pre-calculated for us. So let's apply that and click onto the mass, press F5, and now we're ready to go. Let's click OK. If you've not done already, save this. So I'll save it. Remember, no spaces. So I'll call this mass underscore spring underscore damper. It needs to remain connected. It's one of them pet things with MATLAB that's just incredibly irritating. So I'm going to run it. Whoops, sorry, wrong screen. So if you've run it, what you should find is it keeps flashing on and off. So I'm going to just rewind this and I'll show you why. So come all the way back. Let's get into. So I'm going to click on it and I'm just going to slow the simulation down. If I hit run, you'll notice it's just falling into infinity, which is great. It's what we wanted, because at this point the system has no idea what the mass or the spring, how the relation works. So I'm just going to drag this across. There's a few things about this that will be more clear if I model the mistakes. So let's model in the mistakes and then we can just examine these things. I'll go forces and torques. I'm going to drag and drop a spring and a damper, and I'm just going to rotate that round. What I will do is bring in a connector to here, and I'm going to connect the two across. This connection across is basically saying where the prismatic is acting, you've also got a spring and a damper acting. What we need to do is get these to relate to each other. There is actually an error here, but I'd rather model in the error and then discuss what has actually happened and why. So let's go spring stiffness. I'm going to choose a value of 10 Newton meters, and for damping coefficient I'm going to actually put it at a 0.5 value, so we'll go in fact, yeah, we'll make it even less than that. No, we'll go 5 Newton meters per second, and we go apply. Right, so if you've not done, save it and then run it. Right, if you've done what I've just done, you should find this. This is one of these things, like I think in every single software has these problems. You read them and go, I have no idea what the hell I'm looking at. It makes no sense at all. Do not worry. This is just the pure nature of what this is. So what this is actually saying is, so you're telling me where the center of the mass is, you've got a spring and a damper attached. What it's then saying is, I don't really understand how the physics would even. Right, so it's coming. This is purely because when MATLAB models, if I just zoom this out, when MATLAB models, you'll notice that the mass is here. Now I'm just going to try and turn on the centroids, and they call them centroids, but I just know them as geometric data locations. I think it's just from the CAD thing. So if I click on my frames, look at that. That is a center. What it's actually saying is we've attached a mass and a spring from the middle of the mass, and it's saying that makes no sense, it will not work. So this is simple. What we're going to do is we're going to actually shift this relation by the thickness of what we've chosen. Now we've gone 50 millimeters, so we're just going to go 25. If you think, we're coming 25 in Z, and look at the datum, you'll notice Z is acting upwards as normal. Well, in this case as normal. So you can type this, but I'll pull it out of the library just because it's nice to see where these things are rather than just typing it and rushing. Go frames and transforms, and we have rigid transform. All this basically means is moving geometric references. That's all we're going to do. So let me pull this down. I'm going to make some space for my rigid transform. In it, spin it. We're going to put the base to the follower side of the mass in the spring. So I'm going to connect the two. And if I double click, what you see here is it's basically saying, is there something between this that is related to this that you want relatively rotating or translating within its path? Simply, all we want to do is we want to move in positive Z, because I'll just show you, you can choose positive, negative. It doesn't allow you to literally type in -20 or anything like that. It would be, I personally would think it'd be easier, but I'm not the designers. If I go offset, so let's make it 25, and then let's click apply. Now, if I update this, I'm actually in the wrong Z. That is very frustrating. So let's go back. I'm going to have to move it backwards. Click apply, and then let's try that again. That's better. That's where I wanted it to be. Purely because if I go to my world frame and let's just try running that. So when I run it, what you see is it locates its space. So if I run that, (50-50-50). Right. So what's it telling us? First things first, let's take a look at its movement. Now in these joints, this is where MATLAB in this case really stands in its own right. It's an amazing bit of kit for stuff like this. What we're going to do is let's add a force to it. Let's hit the mass, and then let's see what initially happens. We could do with tuning the C and the K first. Let's just get that right. We'll look at position and velocity of the prismatic joint, because what this will do is it issues, and it will always be relative to the ground, relative to our mass. So if I monitor this, if I probe this particular area, what it will allow me to do is extract things that are going on. So let's double click into the prismatic. Let's do sensing, and under sensing I'll get position, and I can also get velocity. I'll just extract both in this case. Now the one thing that can be a little bit confusing a lot is this operates in three-dimensional matrices, as you'd imagine, because in essence, even though we have what is clearly a two-dimensional element where we're looking to look at how the behavior occurs, this is a three-dimensional space that we can work in, so it will operate in matrices to allow us to look at each element of dynamics. What we're essentially saying to the prismatic is, what we want to do is we want to isolate all the noise, and we just want to extract the key element of this. So in essence, where there are zeros, we're going to cancel these out, and we're going to turn the fuller values into a single set that we can monitor. So what I will do then is I need to go back to my library, and remembering where we got the solver, you've got here, right? Power stream to Simulink converter. Power stream refers to the 3D elements. Simulink to power stream converter, which will essentially make it in acceptable format to come into Simulink. Excuse me. will make it acceptable to come into multibody. What we want to do is extract, so I'm going to left click, drag and drop a PS to Simulink converter. Then I'm going to rotate that around. A quick way of copy and pasting, as one of my students showed me this year. There's always little tools with this. Love it. So right click, keep your finger on it, drag it. It's a quick copy and paste, but if you end up with, I don't know, 20, 30, 40 layers, which you can easily do, doing stuff like that can make life so much easier. So I'm going to connect these two up. So we have position and velocity. If you want units to be applied to the graph as it's coming out, which you all will, I've double clicked into my power stream, which is connected to my P, and you've got output. So if I drop that and then I go millimeters, let's go millimeters, let's see what that does. Now the beauty is, scroll up to the top, let's go to commonly used blocks, let's drag and drop a scope. See, we have the number of inputs, change that to 2, and then let's spin it round. Remember, Control and R, drag it in just across, and let's connect these up. Connect that there and to there, and then let's take a look at what that actually does under the simulation. Now I look there and I think, okay, that's great, but I just can't see the velocity. It's so small in comparison to how much this thing is moving, which is very frustrating. So, because it's actually moved a meter, it's quite a bit. So, what I want to do is go to see where the gear is, drop the arrow, come down. You can change the color if you wish. Where you have layout, I'm going to change that to 2. And if I zoom again, that is what we're looking at. That is massively out of what we're looking for. I think it's beyond critically damped. It almost looks first order. It's like super awful. Anyway, so let's get back onto the spring damper block, and let's just bring in a further value with it. What you can easily do is you can reconfigure this to be respective of what we did in the SolidWorks model. This will still work just as well. So let's run it again. Not sure how it's going to look when it's running, so let's just bring in the simulation and then let's just watch it run. Now, if I open that up, spring's stiffer, obviously. It's holding its state, obviously, as we're looking for. But you see this smooth response. The energy has been dissipated by the spring, but the damper is doing such a good job that it actually instantly grabs it. So I'm going to tune it to be even less. Run it again. And then go even less. Okay. You see these oscillations. We can tune this. I'm just wanting to show you some of the issues that you will face as we're going through this. Right. Zoom into this. Now if you zoom in and if we just pick on a specific area, let's say these areas here. So if I zoom that, and then I'm just going to zoom this area as well. Look at these elements here. This is coming from the time step. The relative tolerance that we're using on our solver is basically making it unsolvable at this point, It's trying to block the points together. Basically, it's plotting these points and then just drawing a line. What we need to do is tighten up that tolerance on the solver. So I'll drop that, and let's tighten that up. Then let's hit it with a force, and then I think that's it. So let's go on to simulation. Let's go model configuration parameters, and under solver, you'll notice now I am speeding up a little bit because we've had a lot of these discussions before. On the relative tolerance, 1 times e to the minus 6. It's quite big, but with that level of refinement, what you'll see is a lot more true representation of the spring active. If I double click in, what we've got now is a nice response. It's what we're looking for. So because we got this, let's bring in further great element on the damper and refine it again. I've just noticed my units are quite big in comparison to my very little block as well. So this is probably some of the reasons why it's been an interesting time tuning this. You'll notice these elements just dropping, the impacts that it's having, that the damping ratio between the stiffness and the mass, once it's been changed, it has, you know, it's easier to get these things. So if I click run again, now on this as well, you'll notice I've run for 10 seconds. Really, if you look here, settling time reads around here. We could refine that. We could just drop that to 8 seconds. But let's just leave that for the minute. If you've not done, make sure you hit save. One final element that I wanted to just check with you is this is just free rate dropping relative to gravity. So if we just take a look at it again, if I just drop it, it will just fall until it reaches equilibrium, which in essence gives us our order responses. Trouble is what about adding a force to it? We can actually have a play around with this. This is very pompous, I know, but when you're doing these, try to keep your lines as tidy as possible, because otherwise it can end up looking like a 5-year-old's drawing. What if I actually actuate this with a force? What if I just hit it once? Now the beauty is on these joints we can do so much more to it, and we will do so much more in some of these videos to come. Notice on actuator, if I drop actuation, motion automatically calculated, which is fine. You'll notice on force it's looking for an input. Well, I can turn it to an input, I should say. So let's go provided by input, click apply. Now what this is the reverse of the power stream to Simulink converter. We're going to go Simulink to power stream converter. So I'm going to go back to my library, scroll back down again. Remember, this was a Simulink this was the power stream to Simulink, but we're going to use the reverse one now. Let's drag that in. Now there's hundreds of ways of doing this, hundreds of ways. I want to make sure my units are right for a start, so let's double click in. On these input values here, you'll notice that I've got a drop. I'm going to drop that, turn that to newtons, and on my inputs here it's asking for an input only. What I'm going to actually do is I'm going to say don't calculate anything, these are zero derivatives. So basically what I'm saying to the system is I don't want you to take anything else from this input. All I want you to give it is a direct force under my commands. So I click zero derivatives, piecewise contact, and we're going to say input, click apply. Now we're ready to hit it with a whatever we like. Many ways of doing this, so I'll show you a couple. If I use constant and if I put a 1 on there, what it will do is it will continuously add 1 at each time over the time step, so it'll end up being 10. That's not really what we wanted. We wanted to look at it, we wanted to hit it with a force and then just let it come to a settling point. not really the best for this. So if I go signals, sources, you've got all sorts here. I recommend just taking a look through all of these. There's so many useful ones here, but what I'm going to do is I'm going to use my personal favorite, which is the signal builder. Signal builder, basically think of it as a line with a value on it, and that's all it sees it as. It's just a line with a value. Until you convert it into something useful, it's just a line and a value. So make sure that when you're feeding something in, you've always got your units right, or else it may feed it in bananas for all we care. Right. So make sure that's there, because MATLAB will just look and go, yeah, obviously it means that, and it will just feed it in anyway. So always be vigilant of this. So if I double click into group, my group 1 signal, that is what we get. So it says over 0 to 10 seconds, from 0 to 4 seconds, there is nothing happening. But if I pull this back, and let's go from 0 to 1 second, nothing happening, and then we're going to hit it with what will be our step. So we're going to hit it with 1 Newton of force, and then after, on 2 seconds, we're going to let it come to rest. So if you've not done it already, save it, because if anything's going to crash, it will be now. So let's just save that, close, and let's open up the mass. Let's open up our plot, and let's take a look at some really cool data sets that it'll give us. So hit run. Now look at this. Not much has changed, but look at this velocity. We get to the point in between 1 to 2 where it starts on a specific road, and then once that force is settled, it then drops off. But it almost, you can see what's happened. You can see that that's occurred there. Really, I mean, we could hit it with a greater force. We could go a lot higher than that. But that was just to give you a demonstration. So if let's open it up and let's have a giggle with this. So let's stretch it up. Let's go to let's go to 50. Let's go 50 newtons. That should give us something entertaining. So bring that in. Let's bring our scope back in. Then let's run again. See there, it gets hit. Huge hits. When we find that, and you see here now. Look at that. Yeah, that's much better. See, it's settled, it starts to fall, and then bang, it's hit. The initial response from the spring is exactly as I'd imagine. It's overstretched, tries to bring it back in. The damper then comes into play, you can see here on the velocity. Then it comes into settle, and then we get a normal settling time as normal. Now, I've shown you that force. You can feed easily feeding road data. If you were looking at a suspension system, you could feed the road data directly in, and you can tune the spring and the damper based directly on the real data that's come off the road, and it's as easy as what we've just done here. It really is that easy. This was just me closing the sets that we've already done on the mass spring damper, but the bigger aspect here is that finally, if I don't show you this, I'm not doing my job right. Units, getting everything out, getting these plots out looking a bit more attractive than what they presently do. In any sort of report, project, thesis, work project, if you're ever using this in work, do not ever take a screenshot of this, because you take a screenshot of this, everybody will say, well, which one's which? Is that position? Is that velocity? What's your units? I'm not clear about anything. So what we'll do, and close that, and I want to put it into something. I'll show you quickly how to extract this, because in some of the former videos that I've just done, I showed you how to make a plot look very attractive, so I'll let you bolt them two together. So you remember in the mass spring damper example, we did workspace. So if I go on workspace, click search, I must find out which model library this is in. Give it a minute. It'll get there. Just click cancel. It's taking us forever. I'll find it. Now, this is one of the frustrations that I've had before. It can often take a long time to find things. Right, see where we have sim out to workspace. I'm going to drag and drop, and I'm going to take it from my position and then hit run. Right, now we've got something to work with. So let's go back onto the workspace. We've got sim out here. I'm going to go plots, and let's plot that. Now this, by the way, see how the units have already been added? All the units have already been placed on. This is actually brand new. Did not used to do this. You had to build everything. So you're practically spoiled. It's great. It's really good. But that is something where I can now export that and turn that into a figure for my reports, or a publishable paper, or whatever you're going to use it for. This now makes it a really, really useful figure for something like that. So that's the final plot. That extracts it directly from SimMultibody. I hope you found this useful. This is now concluding the scripting of the first order and second order system. This is the Simulink model, the Simscape model, and then what we've done to try and add elements in is the SolidWorks simulation in motion, just to try and show that as much as some of you may have been told that SolidWorks is not very good, you'll notice the results I'm getting are identical. The only benefit with MATLAB is we have a lot more solver options. So I hope you found it useful, and see you soon.